All right, let's try out this problem called minimum path sum. So we are given a grid and it's filled with non-negative numbers. We have to find a path from top left to bottom right, which minimizes sum of all numbers along its path. We can only move either down or right. All right, so either down or right. So from 1 to 1, I can see different options. I can go like this, I can go like this, I can go 1, 3, 5, 1, 1, 1, 3, 5, 2, 1, and all of those. Let's take a look at it on a whiteboard. So in the example given to us, this is the array 131, 151, 421. We have to start from here and reach here, and these are the only two directions we can move in. So if I solve for this one, for this guy, the minimum sum, there is only one way to go there. So for this guy, if it's a single element in the array, then the same. For this, it will be 1 plus 1, 2. For this, it will be 2 plus 1, 3, right? For 5, there are two options. It will either 5 plus 2 or it will be either 5 plus 3. Which is smaller? Smaller is 7. For 4, there is only one option, which is 4 plus 3 is 7. For 1, there are two options. Either it goes to this 5 or it goes to this 4, whichever is smaller. Both gave it 7, so 7 plus 1, 8. Essentially, its answer will be 8, right? If I solve for this, there is only one option, 1 plus 2, 3. It has two options. Either it goes to this 7 or it goes to this 3. It will go to this 3, so this will be 6. Now for this one, there are two options. Either it goes to this 6 or this 8. Obviously, it will go to this 6. So the answer is 7. And if you look at the answer, it is 7. So that's the logic. Essentially, we start from the bottom and we keep populating the minimum sum for each and every node. And we don't have to do any repetitions. We just pass through the grid once and that's it. And we can now to change the minimum path sum, we can modify the same input array because or we can create a new one. But I think modifying the same input array should also work. So just let's try that logic. So what we're doing is let's first calculate the rows and column. So n equals to grid length and n equals to 0 dot length. Now we go from top, like bottom right to top left. That's how we'll travel. So for I equals to m minus 1, I greater than equals to 0, m minus minus, and similarly do the same for j equals to n minus 1, j is greater than equals to 0 and j minus minus. Now what do we do? Well, there are multiple cases. You could be on the last row, you could be the last column, you could be the last row and last column, or you could be somewhere in the middle. You have to handle all of those. So if I equals to m minus 1 and j equals to m minus 1, well, in that case, I think I don't really do anything. So I could potentially, well, let's ignore, right? And then else if any one of them, so let's say if only I is equal to m minus 1 and j is not equal to m minus 1, in that case, essentially you are here. So you will add the bottom to you, right? So here you will do grid of ij plus equals to grid of I j plus 1. Else if j is n minus 1. Note that we are updating these minimum path sums. So for there, we don't have to go to the entire thing because this for 5, the right and down are already updated with their minimum path sums, which is what we are updating grid to. So here grid of ij plus equals to grid of I plus 1j. And if it's somewhere in the middle, not in the last row in the last column, then we'll take the minimum of both, right? Okay, so let's do the minimum of both. So we'll do math.min ij plus 1 as well as I plus 1j. And at the end, we return grid of ij. Sorry, grid of 0, 0, right? That's our final answer. What's the time complexity and space complexity? We did not use any more space because we modified the input array. If modification of input array is not required, then we could take an extra array. Time complexity is m cross n. Let's run to see if there are any compilation errors. Right? Accept it. Let's submit to see if all test cases pass. And they do. All right.